welcome to lecture 8. Today I am going to show you the homomorphism theorem. So, let us start. So, last time I have stated the homomorphism theorem. So, if just let us recall that statement quickly. So, in the statement we have seen that if you have a surjective ring homomorphism F from a ring R to a ring S, then this gives you a correspondence between the ideals. So, one side we have the all ideals of R containing this kernel of F, and the other hand side we have all the ideals of S. So, it says that there is a bijective correspondence between these two sets. So, today I will give you the proof of this homomorphism theorem. So, first of all I have to define a map which will if you start with an ideal say I here, and then this map should give you. So, suppose this J is an ideal here, and then I should give you an ideal in S. So, how do I produce an ideal in S? So, the way I can go from R to S is via this map F, which is the given to me, this ring homomorphism. So, that means if you give me the ideal J, then the only way I can land into S by applying this map F on J. So, if I consider F of J, so then I have to check whether it is giving you an ideal in S or not. And on the reverse direction, if you start with an ideal I in S, then I have to produce an ideal in R, but then the only path I am having between R and S is the map F. So, how do I go from this side to R, from S to R? So, I will be sending any ideal I of S via this pre-image. So, pre-image of I is nothing but all the elements in R. When you apply the map F, it belongs to the ideal I. So, this is, let me define, this is nothing but this is the set of all elements in R such that whenever you apply the map F on this element A, then it belongs to the ideal, F of A belongs to I. This is how the pre-image of this element F inverse of I is defined. Now, if I want to show that this is a bijective correspondence, that means what I need to show? So, I need to show the following. So, I want to show that if I start with J, then apply F of J and then apply the pre-image of this, then I should get back my J. And if you start with I and then you come back via pre-image and then you go back via F, then you should get back your I. So, if I am able to prove this too, then this bijective correspondence will be proved. But before proving these two equalities, I need to first check that if you start with an ideal J in R containing the kernel, then its image will again be an ideal of S, and if you start with an ideal here in S, then its pre-image is again an ideal in R. So, let us try to prove that first. So, first step, in the first step I will show you that if J is an ideal, then F of J is an ideal. So, first step I would like to show that F of J is an ideal of S. So, how to prove that F of J is an ideal of S? So, let us start with so, if I want to show F of J is an ideal, then I have to show that it is a subgroup of this abelian group S with respect to addition, and it is closed under the multiplication with the ring elements. So, but I know that a ring homomorphism first of all is a group homomorphism, and via a group homomorphism the image of a subgroup goes to a subgroup. or if you want we can straight away check also. So, let us start with, so let A and B be two elements in f of j. I would like to show their addition A plus B is also in f of j. But since the map F is surjective, so there exist elements x and y in j such that f of x will be equal to A and f of y will be equal to B, because A and B are in f of j. Therefore, f of x and f of y, there should exist elements in j such that f of x is equal to A and f of x equal to f of y equal to B. Now, what is A plus B? A plus B is nothing but f of x plus f of y, and f is a ring homomorphism. So, this I can write is as f of x plus y, but since j is an ideal, therefore, this element x plus y belongs to j, therefore, this belongs to f of j. As j is an ideal, therefore, x plus y also belongs to j. Addition of two elements, because it is closed under addition operation, therefore, x plus y belongs to j. Next, we will prove that it is closed with respect to multiplication from the ring element. So, let S belongs to S be any element. So, let S be any element in S and be any element I am considering in S. Then I would like to show, and suppose A is any element in f of j, then I would like to show that their product A s is again in f of j. But since I am having that this map is surjective, so since f is surjective, so there exists some element say R in R such that f of R will be equal to S, and there exists some x belongs to j such that f of x will be equal to A. Since A is in f of j, therefore, there will be some element in j that I am calling it to be x such that f of x will be equal to A. Now, if you want to see, so I would like to show, so I wants to show that S into A belongs to f of j. But what is S into A? S into A is nothing but f of R, and A is f of x, and f is a ring homomorphism. Therefore, this is nothing but f of R into x, and since j is an ideal in R, therefore, R x belongs to j, therefore, this belongs to f of j. So, this is happening because as j is an ideal of R, therefore, this R time x belongs to j again. So, this is by the property of the ideal that we have used here, and we have shown that if you start with an ideal j, then f of j is in fact an ideal of S. Now, I will show the next, that is step 2. So, second step. So, second step I will be showing that if you start with an ideal I, so I is an ideal of S, then I wants to show that its pre-image, which is nothing but the collection of the elements in R such that f of A is belongs to. So, this is all elements in R such that f of A belongs to I. So, this is an ideal of R containing kernel of F. This is what now I would like to show you. So, let us see. So, since I need to show that this F inverse I is an ideal. So, let us try with two elements. So, let A and B are two elements in the pre-image. I would like to show that their addition will also be in the pre-image. Now, since A and B are in F inverse I, that means f of A and f of B is in I. Now, if you look into f of A plus B, then since it is a ring homomorphism, f of A plus B is nothing but f of A plus f of B, and f of A, f of B both belongs to I, and I is an ideal. Therefore, it is closed under addition operation. Therefore, this belongs to I, which implies that A plus B is in the pre-image of I, because under F it belongs to I. So, now this is closed under addition operation. Next, I will show that it is closed if you multiply with the elements from the ring. So, let R be an element in R, and this A is an element in the pre-image of I. Then I want to show that R A will be in the pre-image of I. So, let us see. F of R A is what? F of R A is nothing but f of R into f of A, and by definition f of A belongs to I, and I is an ideal. Therefore, this belongs to I. As I is an ideal, therefore, f of R into f of A belongs to I. So, it proves that it is closed under. So, that means this says that R into A belongs to the pre-image of I. Therefore, it is closed under multiplication from the elements of the ring R. So, hence it proves that this pre-image of I is an ideal of R, but I have to show that this is an ideal which will contain the kernel. So, next I would show that it contains the kernel. So, let us start with any element, say x is in the kernel of F. If x is in the kernel, that means what? Under the map F, this element x is mapping to 0, 0, this is the 0 in the ring S. So, this since I is an ideal and 0 always belong, because I forms a subgroup, therefore, the additive identity will always be in the ideal I. So, this means that this f of x belongs to the ideal I, therefore, it implies that x belongs to the pre-image of I. So, what I have shown here, if you start with any element x which is in the kernel, then we are able to show that that element is in fact in the pre-image of I. That means that kernel is sitting inside this pre-image. This shows that kernel of F is sitting inside that pre-image of I. That means, if I start with any ideal I in S, then its pre-image is not only in fact an ideal of R, it is in fact an ideal which contains the kernel. So, I have proved that if you start with an ideal. So, let me just go back quickly, and what are the facts I have proved so far is the following, that if I start with an ideal J, then it says that if I map then it says that if I map J to f of J, then this is in fact a J getting mapped to an ideal f of J, and if you start with an ideal I, then its pre-image f inverse of I is also an ideal in R which contains the kernel. Now, I will show that these correspondence is 1 1 and on to, that means bijective. So, for that I need to show this following statement, that if you start from j, then f of j pre-image of that will be equal to j, and if you start with I, take the pre-image and then take image, then it will be equal to I. So, let us try to prove that. That is the third step. Before proving, let us observe the following thing, that this ideal. So, it is clear that this containment J is always sitting inside f inverse of f of j. This is quite obvious because of the structure of this one. Now, I will prove the reverse containment. So, I would like to show that f inverse of f of j is sitting inside j. So, in order to prove that, let us start with an element A in f inverse of f of j. So, this implies that f of A belongs to f of j. Now, this means what? That this means that f of A can be written as f of some x for some x in j, because this is in f of j. So, now this says that f of A minus x is equal to 0. This is by the property of the ring homomorphism and so on. So, now this is nothing but this implies that A minus x belongs to the kernel of f. But what do I know? That kernel of f is an ideal containing j, because I have started with an ideal which contains the kernel. So, j was an ideal in the set which are ideals of R containing the kernel. Therefore, j contains this kernel, and then from here I can say that this, since x is also in the kernel, therefore, this A belongs to j. This is because x belongs to this x belongs to j and A minus x belongs to j. Because of this reason, I am observing that A is also in the ideal generated by j. So, A is in the ideal j. Therefore, you can see I have started with an element A which was in f inverse of f j, and I have proved here that this A is in fact belongs to j. So, this implies that f inverse of f of j is sitting inside j. So, this proves the following fact. So, let me write it down. Therefore, we have proved that f inverse of f of j is nothing but equal to j. So, this is I have proved. So, now, but this proof is not yet over, because I have to show that if you start with an ideal I in S, and then if you consider the pre-image and then again you go back to S via F, then you will get back your I. So, that is the next thing that I would like to show. So, for that, so let us next I would like to show that f of f inverse of I is equal to I. So, in order to prove that, let us see one of the containment is easy to see. So, which one is easy to see? So, note that this containment is obvious. Which one? That f of f inverse of I is contained in I. So, I will prove the reverse one. So, let us start with, so let me just say, wants to show the other one, that means I is sitting inside f of f inverse of I. That is what I would like to show next. So, let us start with any element A in I. Now, since this map is surjective, so I will get a pre-image in R. Okay. So, since F is surjective, there exists an element x in R such that f of x will be equal to A. But this implies what? This implies that x belongs to, since f of x is equal to A, that means x is in the pre-image of this element A. So, x is nothing but this is in A belongs to this ideal I, therefore, x is in the pre-image of I. So, this implies nothing but that A belongs to f of f inverse of I. So, with this I am able to show that this equality holds, therefore, f of f inverse of I is equal to I. So, next, so this completes the proof of the homomorphism theorem. Next, we will see some nice application of this homomorphism theorem. So, let us go to the following proposition. So, consider the natural surjective ring homomorphism. So, consider the natural surjective ring homomorphism from a ring R to a quotient ring R quotient I, where I is any ideal in R. So, let me denote this natural map by pi. So, our next aim is to relate the ideals of this quotient ring R quotient I with the ideals of R. So, we will be using this homomorphism theorem between the two rings. One side we have the ring R, on the other side we have the quotient ring R quotient I, and we will be trying to relate this ideals between these two rings. That means, how the ideals of this quotient ring are related with the ideals I. So, this theorem says that, okay, let me, where I is an ideal, in that case we can say by previous theorem. So, by previous theorem we can say, if we apply that there exists a bijective correspondence between the two sets. I am just applying the homomorphism theorem now in between these two ring. One side I have R, another side I have this quotient ring R quotient I. So, what does it say? It says that the ideals of R containing the kernel of pi, but what is the kernel of pi? Kernel of pi is nothing but the ideal I, right, because all the elements of I are going to 0. So, it says that the ideals of R containing I, these ideals are in 1:1 correspondence with the ideals of the quotient ring R quotient I. So, these are in 1:1 correspondence with the ideals of R quotient I. Therefore, it gives you that for every ideal in this quotient ring R quotient I, there exists an ideal in the ring R containing I, and on the other hand, for every ideal R containing I, there I will get an ideal in R quotient I. So, it identifies or characterizes all the ideals of R quotient I, or how does they look like. So, as a corollary to this one, I can say that ideals of R quotient I is of the form, I can say they are of the form, say J quotient I. How does this look like? The ideals, the elements are of the form A plus I, such that A is varying over J, where J is an ideal containing the kernel I. Containing the ideal I. So, it characterizes how does the ideals of this quotient ring look like. It will be of the form J quotient I, okay, where A is the elements will be of the form A plus I, A is varying over all the elements of J, and note that J is an ideal which will contain this ideal I. So, this characterizes the ideals in the quotient ring. So, it is very important characterization. With the help of this one, I will be able to describe all the ideals in the quotient ring R quotient I. Now, I will state the following theorem, which is also very useful. So, let F from R to S be a surjective ring homomorphism and J contained in S be an ideal of S. So, J is an ideal of S, then it is saying that this pre-image we have already seen is in fact an ideal of R, is an ideal of R, and I will be having this isomorphism that R quotient F inverse of J is isomorphic with S quotient J. The proof of this is very short. In fact, it follows from what we have already seen using the first isomorphism theorem. So, you can see that I have this map from R to S, which is the map F given. This is a ring homomorphism. J is an ideal. So, I have this natural surjective map from S to S quotient J that I denote by pi. Then, if I talk about this composition, then you can see that pi composition F is a map from R to S quotient J. This is a composition of two ring homomorphism, therefore, this is again a ring homomorphism. So, this pi compose F is a ring homomorphism, and not only that, this is also a surjective ring homomorphism because F is surjective and pi is surjective. And what about the kernel of this composition? If you look, the kernel of this composition is nothing but all the elements in R such that their composition, that pi compose F applied on A is equal to 0. So, 0 where? 0 in the quotient ring S quotient J. So, if I write down, then all the elements in R such that F of A belongs to J. Therefore, this is nothing but the ideal pre-image of J. Therefore, if I apply first isomorphism theorem, then I can see, therefore, by first isomorphism theorem, all the hypotheses of first isomorphism theorem are satisfied. So, therefore, by first isomorphism theorem, we have that R quotient, the kernel, which is nothing but the pre-image of J, is isomorphic with S quotient J. So, this proves this isomorphism between these two rings, and as a quick corollary to this theorem, we can observe the following. So, let us see. So, let us have pi be the natural surjective map from R to R quotient I, be the natural surjective ring homomorphism So, what is this ring homomorphism? Pi of any element A, I am sending it to the corresponding left coset. So, this is the homomorphism I am having, this is, and let J is an ideal containing I be an ideal of R. So, J is an ideal. So, if you can see the kernel of this homomorphism, pi is nothing but I and J is an ideal containing this kernel which is I. Okay. Then this pi inverse, the pre-image of this ideal J quotient I will be nothing but the ideal J, right. So, I can talk about this in this quotient ring I have this ideal. So, I have this quotient ring R quotient I, and in that quotient ring I have already observed that the ideals of this quotient ring are of the form J quotient I. So, I am considering the ideal J quotient I in this quotient ring R quotient I, and then the pre-image of this ideal, okay, J quotient I is nothing but J. So, by first by this previous theorem, what I can say now, that this is nothing but isomorphic with R quotient J. So, then by previous theorem, we have this isomorphism. So, here you can see that the ring I am considering here is the quotient ring R quotient I, and the ideal that I am considering, we have already seen that the ideals of R quotient I are of the form J quotient I, where J is an ideal of R containing I. Therefore, this is the ideal I am considering. So, if you want to relate with this one, then you can see that S here is nothing but R quotient I and J is nothing but J quotient I, and then via this previous theorem I can say that this R quotient, the pre-image of J quotient I, which is nothing but the ideal J. Therefore, R quotient J is isomorphic with R quotient I quotient J quotient I. So, this is the one of the useful theorem that we will be useful fact that we will be using later also when we are operating we are doing operations in the quotient ring. So, with this I will finish today's lecture, and these are the references that for today's lecture.